5 minutes right now. Okay, so good morning, Professor Oluri. We are CivilAxis Engineering. My name is Carlos Leon, and I'm presenting today with Luis, Daniela, Julian, and Rafael. Our project is the preliminary geometric design of a new roadway alignment in Forsyth County, Georgia. The proposed roadway, which we identify as SR140 project, connects SR20 at the southern end of the project area to an existing dirt road at the northern end. The main goal was not simply to draw the shortest road between those 2 points. We had to create an alignment that was safe, practical, and compatible with the existing terrain. We also had to consider wetlands, drainage crossings, existing roads, environmental impacts, and earthwork, and require bridge and culvert. And well, during this presentation, we will explain how we selected the preferred corridor and how we develop and check the horizontal alignment, super elevation, the vertical alignment, the earthwork, and the drainage requirements. So first, the agenda. We organized the presentation in the same order that an actual preliminary roadway design will be developed. We will begin with the project need and the main goal design controls. After that, we will explain the sign constraints and the 5 alternative routes considered by the team. And we will then show how corridor selection matrix led us to choose the black route. And once that route was selected, we develop it in Civil 3D and evaluated the horizontal curves, the super elevation transitions, the vertical alignment, the horizontal and vertical coordinates, the earthwork, and the drainage. Well, finally, we will present a recommendation and also discuss the parts of the design that will need additional refinement in the next phase. So then will come the project need. The roadway is intended to operate as two-lane rural minor collector and is supposed to provide a safer, more efficient connection between SR20 and the existing road while serving the surrounding rural and developing areas. The project is located in a rolling terrain. Because of that, a completely straight alignment will not necessarily be the safest or least expensive solution. It could cross steep slopes, produce excessive cut and fill, or interfere with the wetlands and drainage channels. To understand the site, we will first study the provided topographic surface. In Civil 3D, we displace the existing ground using elevation banding and slope banding. With these views, this view basically allow us to identify steep areas, high and low elevations, water features, and locations where construction would likely require major grading. The proposed alignment also had to match existing elevations at the beginning and ending points and near the subordinate roadway intersection. These requirements made route selection an important first step before beginning detailed curve calculations. And now, well, I will pass the presentation to Luis, who will explain the design control and how we evaluated the site and roads alternatives.
Hello, Professor Aluri. So this is Louis. I'm going to continue with the slide of design controls. Thank you, Carlos, for the introduction. So before developing the alignment, we established the geometric design controls from the project scenario and the roadway design criteria. The roadway was classified as a rural minor collector with one 12-foot lane in each direction and a 6-foot shoulders. The minimum design speed is 40 miles per hour, while the maximum design speed is 45 miles per hour. The speed range was used to avoid both under-designing and unnecessarily over-designing the roadway. The maximum permitted super elevation is 8%, and at the beginning and intermediate roadway intersections, the alignment should meet the existing road at approximately 90 degrees, with an allowable difference of plus or minus 10 degrees, and the profile grade at those intersections should also remain within plus or minus 4%. The project requires one major bridge or drainage structure with a maximum length of 200 feet and one small culvert. The major structure should be located on a straight portion of the horizontal and vertical alignment wherever practical. Um, this is because constructing a bridge on a curve would increase complexity and cost, and these controls became the basis for evaluating every alternative and for developing the final geometry in Civil 3D. If Carlos can move on to slide 5.
Oh yeah,
Thank
just
you.
give me a second. Oh, so sorry, guys. Okay, there you go. Next slide. Mhm.
Okay. So on this slide, we're going to talk about the existing site entrance. This slide shows the elevation and slope information that we generated from the existing ground surface. Um, the elevation banding separated the site into elevation ranges, while the slope banding highlighted areas where the terrain changes more sharply. We used these maps together with the contour lines to identify exclusion areas and areas of concern. The strongest exclusion areas included wetlands, water bodies, and locations with terrain that would be extremely difficult or environmentally undesirable to cross. Other areas were classified as a critical concern areas, and construction in those areas was possible, but it could require larger cuts, fills, retaining measures, additional drainage work, or erosion protection. We also identified the required control points. These included SR20, the northern dirt road, the subordinate existing road, and the major drainage channel that required a bridge or large structure. This analysis helped us avoid selecting a route based only on visual directness. Instead, we considered how the alignment would interact with the complete terrain and the drainage system. And then moving on to slide 6, I'm going to talk about the alternatives that we considered while on the process. So, using the exclusion areas, concern areas, and control points, we developed 5 routes alternatives: red, yellow, white, purple, and black. The red route was one of the most direct alternatives. However, it crossed more challenging terrain and it would likely produce greater grading and constructability problems. The yellow route avoided some steep areas, but it required a large detour that increased the roadway length and then reduced its efficiency. The the white route was considered our main backup alternative. It had moderate curvature, but it did not provide a clear overall advantage compared with other routes. The purple route avoided some difficult areas, but it was less direct and included more changes in direction. The black route provided the best overall balance. It remained relatively direct, stayed near the central portion of the site, and avoided many of the most difficult topographic environmental areas. We did not end up making the final decision based only on our visual opinion. We scored our every route using a corridor selection matrix, which Daniela will explain next.
Okay, so I'm going to be talking about the corridor selection matrix. Thank you, Louis. To make the route selection process more objective, we evaluated each alternative using 5 different criterias: directness and length, environmental impact, safety, cost, and the scenic quality. Each route received a score um, for each of the 5 criterias. We then added the scores to obtain a total for each alternative. The black route received the highest total score with 20 points. The red route received 17 points, and it was the second highest alternative, but its greater terrain and constructability concerns made it less balanced. Purple received 14, white 13, and yellow received 11. The black route did not receive the highest score in every individual category, but it performed consistently well across the full group of criteria, which is why it became the preferred corridor. This is important because route selection involves trade-offs. The best route is not always the shortest route. It is the route that provides the strongest overall balance between safety, environmental effects, construction difficulty, cost, and roadway operation. After selecting the black route, we converted the proposed tangents and points of intersection into a Civil 3D alignment. So this is pretty much how we selected the alignment. We began the alignment selection at 1,000 at station 1,000 and ended it at station 10,361. By subtracting the beginning station from the ending station, we obtained a total roadway length of 9,361.99 feet, which is approximately, give or take, 1.77 miles. The team obtained the coordinates of the beginning point, ending point, and intermediate PIs from the topographic plan. We entered those coordinates into Civil 3D to construct the roadway center line accurately rather than drawing it freehand. The selected center line generally follows a central path through the project area. It moves around difficult terrain where necessary, but avoids adding excessive roadway length. The final alignment includes 4 circular horizontal curves. Tangent sections were also preserved near the roadway intersections and near the major drainage crossing. Now for the horizontal alignment. The horizontal design to design it, we use the radius of 1,250 feet for all 4 of the curves. We first calculated the tangent bearings and the deflection angle for each PI. Using the selected radius and deflection angle, we were able to calculate the tangent length, curve length, middle ordinate, PC station, and PT station. One curve was checked actually all by hand, and then the remaining of the other 3 were organized in a table. After creating the alignment in Civil 3D, we generated the alignment curve and station reports. We compared those Civil 3D results with our calculations to confirm the radius, curve length, tangent length, bearing direction, and stations. So curve 1 is a right curve with a length of approximately 555 feet. Curve 2 is a left curve, and it's the longest curve with a length of approximately 1,250 feet. Curve 3 is a right curve with a length of about 719 feet, and curve 4 is a left curve with a length of about 863 feet. Using the same 1,250 foot radius throughout the alignment, created consistent and relatively conservative horizontal geometry for the 40 to 45 mile per hour design speed range. We also checked that the design did not contain broken back curves. Although the curve directions alternate, the reverse curves are separated by tangent sections, which actually gives drivers time to transition between the curves. I will now pass the presentation to Julian, who will discuss superelevation, vertical alignment, and horizontal and vertical coordination.
Thank you so much, Dana. I will be talking about now super elevation. Once the PC and PT stations of the horizontal curves were established, we calculated the super elevation transitions. The maximum permitted super elevation was 8%. However, because of our selected radius was 1,250 feet, the required design super elevation was only 4%, which remained safely below the maximum. For each curve, we calculated super elevation runoff length of 190 feet and a tangent runout length of 50 feet. The tangent runout is the distance used to transition from the normal crown to zero cross slope. The runoff is the distance used to continue rotating the pavement until the full super elevation is reached. We calculated the critical stations for the beginning of the tangent runout, 0% cross slope, 2% cross slope, and beginning of the full super elevation, end of full super elevation, and return to normal crown. These results were then entered and reviewed in Civil 3D. We compared the available tangent distance between consecutive curves with the transition requirements and transitions that did not overlap, which confirmed that there was not enough separation between the curves. Now I'll be talking about vertical alignment. After completing the horizontal geometry, we generated the existing ground profile along the alignment in Civil 3D. We placed the vertical points of intersection so that the purpose profile would follow the rolling terrain while connecting the required elevations at roadway tie-ins. We then connected the grade tangents using parabolic, crest, and sag curves. The proposed profile contains 8 vertical curves, 5 sag curves, and 3 crest curves. We used a K value of approximately 80 feet per percent of grade change. The maximum proposed grade is 5.6%. The table summarizes the incoming grade, outcoming grade, curve length, and the high and or low point of each curve. And a sample verification, vertical curve 1 has an entering grade of 0.36% and an exiting grade of 4.27%. The algebraic grade difference is at 3.91%. Multiplying the K value of 80 by 9.31 gives a curve length of 312.80 feet. The PVI is at station 27 plus 36.42. Subtracting half the curve length gives a PV station of 25 plus 80.02, and adding half the curve length gives a PVT station of 28 plus 92.82. These results match the Civil 3D PVI station and a curve report. Now going on to horizontal and vertical coordination. When we then compared the horizontal curves controls with the vertical alignment controls. This check is important because drivers experience horizontal and vertical changes at the same time. Poor coordination could make a curve difficult to read or could hide part of the roadway from the driver, causing possible accidents. Several of our horizontal and PC and PT stations are either directly aligned with the vertical PVIs or located very close to them. For example, horizontal curve 2 ends at a station 56 plus 00.83, and vertical PVI 4 is also located at station 56.00.83. Horizontal curve 3 begins at station 67 plus 7.15, while vertical PVI state 5 is at station 67 plus 0.8.12. Those stations differ by less than 1 foot. Horizontal curve 3 ends at approximately station 74 plus 26, while vertical PVI 6 is approximately station 74 plus 24. The controls for horizontal curve 4 is also correspond closely with PVI stations 7 and 8. These station comparisons show that the profile was not developed independently from the horizontal alignment. These two were coordinated to provide a more consistent and understandable roadway path. Now, Rafael will now finish the presentation by discussing earthwork, drainage, and our final recommendation. Thank you.
Thank you, Julian. After completing the horizontal and vertical alignment, we created a roadway assembly and used it to build the Civil 3D corridor. The assembly include the 12-foot lane, 6-foot shoulder, pavement structure, and daylight slope. We then created sample lines along the corridor and compared the proposed corridor surface with the existing ground surface. Civil 3D calculated the cut and fill volumes using the roadway cross-section along the line. The volume report produced approximately 477,104 cubic yards of cut and 205,780 cubic yards of fill. Subtracting the fill from the cut gives a net excess cut of approximately 271,324 cubic yards. Assuming that each truck can carry approximately 20 cubic yards, disposal or relocation of the excess material will require approximately 3,567 truckloads. The mass ordinate diagram shows that the project initially requires fill, but the alignment later produced substantial excavation and finishes with a large slurpus of cut material. The mass ordinate diagram shows that This is the main constructability weakness of the current design. It does not make the select corridor unacceptable, but it shows that the vertical profile should be optimized during the next design phase. Small adjustments to grades and vertical curves location could potentially reduce excavation, hauling, disposal, and overall construction costs. Now, talking about the drainage was considered during route selection and during development of the final alignment. The scenario requires one major bridge or large drainage structure with a maximum length of 200 feet and one small culvert. The alignment maintains a relatively straight section near the major drainage crossing, which is beneficial because a straight bridge is generally simpler and less expensive to construct than a curved bridge. The smaller culvert will carry another natural drainage path under the roadway. The drainage area and direction of flow were examined using the topography and Civil 3D surface. For final design, the exact bridge limits, culvert, station, catchment boundaries, and hydraulic capacity will need to be confirmed. Our work represents a preliminary geometric design rather than a final hydraulic design. The plan and profile sheets combine the major design information in one place. They show the roadway center line, bearings, curve data, stations, existing ground profile, proposed grades, vertical curve information, and the location of structures. Um, Based on our complete evaluation, CivilAxis Engineering recommends advancing the black route into the next level of preliminary design. The black route received the highest corridor selection score and provides the best overall balance amongst the alternatives. The alignment connects the required roads, avoid the most severe size constraint where practical, and provides a route length approximately of 1.77 miles. The horizontal alignments use four 1,255-foot radius curve, which provide consistent geometry for the select design speed. The required elevation is below the project maximum and the transition do not overlap. The vertical alignment contains 8 properly connect crest and sag curves, and several vertical controls are coordinated closely with the horizontal curve controls. The main issue that still requires improvement is earthwork. The present profile generates a significant amount of excess cut. Drainage and structure location are also require finally hydraulic verifications. Overall, these are designs refinements rather than reasons to reject the selected corridor. The black route remains the stronger preliminary alternative because it provides the best combination of safety, directness, environmental sensitivity, and constructability. Thank you for your time. We are Civil Access Engineering, and this concludes our presentation.